Take every fundamental particle in the universe, electrons, quarks, neutrinos, and dump them into a giant blender. If you hit puree, logic suggests the result would be total random chaos, a microscopic demolition derby where everything smashes together and morphs into whatever it wants. But if you zoom in on the subatomic level, you find a strictly regulated system. Particles can collide trillions of times a second without ever randomly fusing or mutating into new, impossible forms. An electron and a positron can annihilate each other to produce a photon of light. That is an allowed interaction. But an electron colliding with a proton will never spontaneously fuse into a single new hybrid particle. The universe forbids it. In the mid-20th century, physicist Richard Feynman decoded the hidden architecture behind these collisions. He translated the rules of particle interactions into a visual language. Every line, angle, and connection in a Feynman diagram represents a specific, rigorous mathematical calculation for a permitted physical event. These geometric maps operate on a hidden accounting system. We call the individual entries in this ledger quantum numbers. To understand how these rules work, we have to look at the grammar of the diagram. The most critical feature is the vertex, the exact point in space and time where lines meet and an interaction takes place. For an interaction to successfully pass through a vertex, a strict numerical ledger must balance perfectly. Every property entering the interaction must be accounted for in the state that leaves it. Electric charge is the first entry on that ledger. If an electron enters the vertex carrying a -1 charge, the combined charge of everything leaving must also equal -1. Here, the electron leaves with its -1 charge, accompanied by a neutral photon carrying 0 charge. The universe also tracks identity categories, like lepton and baryon numbers. Electrons carry a lepton number of +1. If a +1 lepton enters, a +1 lepton must exit. This accounting ensures particles cannot spontaneously swap species or turn into different classes of matter. If we try to draw a vertex where an electron turns into a quark, the ledger fails. The incoming lepton number is 1, but the outgoing lepton number is 0. If the quantum number ledger is off by even a fraction, the interaction is physically impossible. These same rules define how forces push and pull at the microscopic scale. Particles experience forces by throwing and catching force-carrying particles called virtual bosons. Particles can only emit or absorb specific bosons if they hold the correct quantum number currency. A charged electron easily trades photons with its neighbors to feel the electromagnetic force. But a neutral neutrino lacks that currency. The photon passes straight through it without interaction. The strong nuclear force uses a virtual particle called a gluon. To participate in this exchange, a particle needs a different quantum number called color charge. Quarks carry this specific tag, allowing them to bind tightly into protons and neutrons. The weak force is the rare exception. It possesses a special clearance that allows it to change a particle's internal identity, a property physicists call flavor. These quantum numbers serve as a global permission system, dictating exactly how the universe is allowed to push, pull, and bind itself together. This same accounting system defines the internal structure of stationary matter. A property called spin sorts every particle in the universe into one of two categories: the force-carrying bosons or the matter-building fermions. In 1925, physicist Wolfgang Pauli realized that the half-integer spin of fermions creates a rigid geometric boundary for how matter can be arranged. This is the Pauli exclusion principle. Because electrons are fermions, no two electrons can occupy the exact same space with the exact same set of quantum numbers. Once the slots in the lowest orbit are full, additional electrons are forced into a wider, higher orbit. This single rule gives matter its physical volume. Because their outer electrons cannot share identical quantum states, atoms repel each other, establishing the distance required to take up three-dimensional space. Without quantum numbers to enforce this exclusion, every electron would immediately fall into the lowest possible energy state. Matter would collapse into a featureless microscopic soup. By regulating everything from a subatomic collision to the solidity of a chair, quantum numbers serve as the immutable code that defines the physical boundaries of reality.